Okay, I think we can go ahead and get started. It's about 5 after. So welcome everybody to the virtual EPR seminars. Today, our speaker is Sylvain Bertaina. He's had a long and illustrious career in quantum magnetism and qubit spins. He started his PhD doing EPR and quantum spin chains before moving on to a postdoc in quantum coherence in rare earth or lanthanide materials. He did a second postdoc at the National High Magnetic Field Lab in the US, in Florida, constructing EPR spectrometers that work at millikelvin temperatures before moving to CNRS, where he started as a researcher before moving to group leader and is now a research director at the very cool facility he was just describing, this infra-analytics, which maybe he will repeat himself and tell us those cool details about the high field stuff they can do there. But we're happy to have him today, and he's going to tell us some information about quantum spins using EPR.
Okay, thank you, Joseph. Thank you for the invitation and this presentation. So let's start with that. And you should see my screen correctly.
Yes, looks good on the side.
Okay. Up. Okay, so my talk today will be about the quantum information processing, but especially the role of electron paramagnetic resonance into this new topics, not new now, but weird topics for a lot of us. And it will be a mix between kind of lecture and some result we have in the last years, decades now in the field. So what is quantum information? So quantum information is the equivalent quantum of classical information. In the classical information, you code information in 0 or 1, and it's well defined. 0 is a 0 and 1 is a 1. And you can store the information, and all, I would say, so far, 100% of electronic is based on classic information. But if you manage to use one of these bits and to use the superposition of state, the principle of superposition of state, you can code much more information. For example, here, if you have only one bit which become a qubit, you can code 4 and 5 at the same time. And imagine you can do that with all of the qubit, and you can increase the amount of memory and your amount of information you can work with. But how to do that? But actually, pretty simple. In theory, you need a state you can put in superposition and coherence. So in our case, we will use a quantum compass, and the quantum compass is the electron and the spin of the electron. And using spectroscopy, you can code the information. So first, you can code by 0 or 1, click by inversion of magnetization, but it's still, in this case, it's still classical information. But if you manage to create a superposition of state with south and north at the same time, your quantum compass become a qubit. It looks simple. The problem is the whole universe want to destroy your system. And this is what we will see in the future. But one of the parts to use spins and qubit as for stock information is quantum memory. Imagine you can entangle 300 qubits, which is far from being the state right now. It's like you can code this number of information. I didn't choose 300 randomly because 2 exponent 300 is equivalent to the number of atoms in a universe. So that's means with only 300 perfect qubit entangled, you can code as much as information you have of atom in a universe. So that's look fantastic. Right now, it's more fiction than science, but anyway, it's maybe the future. So some example. So the legacy of the qubit, superconducting qubit. This is what is inside the almost working quantum computer developed by IBM, Google, and other companies. And another one which worked in the past, but now it's for it's lost. It's NMR, so using nuclear spin, and they managed to code information in one molecule. But this is for the past. For the present and the future, a lot of company and startup develop its own way to create a quantum computer or quantum calculator. This is one of the main road with quantum circuit, cold atom, ions, topological qubit, and these things I don't even know what is it, but is the future. In our case, but we work with electron and electron spin qubits. So some of the state of the art of electron spin qubit, you can have the NV center in diamond. It works perfectly. You have now some quantum sensor working at room temperature. For quantum memory and quantum transductor, you can have rare earths inside optics crystal. And also, because we are all the industry and the electronic is based on silicon, you can also use silicon as base for developing quantum bit. And it works, it's not so bad. It's really difficult to entangle this such kind of qubit, but we are developing such approach of creating electron spin qubit. So now what is a quantum computer? This is Outlook quantum computer from Google or IBM. Or they sell it as a quantum computer, but actually it's a fridge. It's only a fridge with a lot of wires. But as you can see, you have to go at very low temperature, so they have this kind of fridge. But actually what is inside a quantum computer, it's an ESR spectrometer, except the spin, it might be a bit different than the electron spin, but it's an electron spin resonance spectrometer. Of course, they don't use the first one, but they use something, and we can use something similar to the Bruker system. And actually, in the future of this presentation, I will only present results done in Bruker and conventional spectrometer. We have also results in the homemade spectrometer, but the purpose here is to prove with a commercial spectrometer and EPR spectrometer, you can find a lot of interesting property of electron spin resonance, electron spin qubit. So now, what is about electron spin resonance? Well, I'm sure you know it, but the main equation that ruled my life for the last 20 years now, it's the Bloch equation. When you have a spin inside a field, a magnetic field, it presses around the axis of the field. And if you had a microwave and some damping, you have a kind of oscillator, a damped force oscillator. And if you solve this three-dimensional derivative equation, you have two regimes. One is the transient regime, or in our case, the pulsed EPR regime. And if the damping is too big or the time is too long, quickly you attain a steady state regime or incoherent regime. This is more the continuous wave EPR. But again, this is a simple spin with a symmetry of spin. And if we change the field by a gravity field, we can use also mechanical spin to explain what's happened. And this is here with my assistant. If you have a mechanical spin inside the gravity field, your spin presses around the field. And if you put your spin in intermediate state, you have superposition. And of course, without relaxation, the system stays in resonance. So this is the same physics. Here it's more practical and with the mechanics, but it's the same kind of science. Without relaxation, we can have a superposition of state, not really natural, but it's steady. Also, you have the choice of the frame. If you watch the spin from the laboratory frame or inside the spin frame, you don't have the same complexity. And this is the same thing that you can have in astronomy. When you have the trajectory of Mars or March around the Earth, it looks really difficult. But when you transfer the Earth frame to the Sun frame, it's much more simple to describe the trajectory of planet. And this is the same thing with spin. If you are in the laboratory frame, but your spin has a complex trajectory, but if you are in the rotating frame, the same, you have a very simple trajectory, and actually all pulse EPR spectroscopy is made on this rotating frame. So now the thing is, we don't want to lose our quantum coherence because we play a lot with in the time before the relaxation. What are the two main source of destruction of quantum information? First of all, the T1, so the relaxation along Z, mainly due to the spin phonon, and the decoherence in the plane, mainly due to the noise of the field. You can also describe the source of decoherence by this picture with the central spin and the neighboring spin, but usually for when I present for in the broad audience what is decoherence, I explain spin are like I like student. If you have too much student at the same place, they relax quickly. So the idea is to reduce the quantity of spin in the media by separation, so by magnetic dilution, doping material or frozen solution. If you have a student from another group, it tends to perturb your student, so you have to remove it or reduce the quantity of nuclear spin. So this is for the hyperfine interaction and super hyperfine interaction. And of course, the temperature. So, and you know, in Marseille, we have a lot of source of relaxation, but by decreasing the temperature, you can remove the source from the phonon, which will relax your system. So when you do everything like that, it's more boring, but it's time to play with your spin. And this is what we will do right now. So my first example, I will have 3 examples, not the most common, but we'll try but at least you can do that in your own spectrometer if you want. The first is the coherent control using EPR, and the particular example is a QDIT. So what is a QDIT? A QDIT is more than 2 level for a qubit. Qubit is 2 level, and when you have more than 2 levels, it's called QDIT. Actually, it looks like a large spin, as you can see. And this description is for superconducting qubits. So you see it's not from the spin. And this is a quantum circuit. Nobody really understands that. But when you see that, it looks like a manipulation of state we can have in EPR. And indeed, this is what we will try to do. So some example of QDIT, you have the Transmon, so which is a superconducting system from IBM. You have a trapped ion, when you can trap cold ion in chain and create a multi-level qubit. And this one is molecular magnet. It's a double decker of tallocyanine with 2 terbium, and you can have access to 16 level. So this is for other common QDIT. In our case, it's even more simple. We have used MGO. MGO is certainly the most simple system. You certainly have some in your lab. It's a caliber. Naturally, it contains manganese, but MGO is cubic. So that means there is not a lot of anisotropy. And manganese is spin 5-half. So that means at least 6 level. But you have also the nuclear spin. So you might have up to 30 line at first order. So we used this manganese, and we start with what? But we start by seeing, is it possible to manipulate more than 30 transition? But actually, yes, it has been proved a long time ago. And what's happened is usually in the linear theory of EPR, the allowed transition is delta ms equal plus or minus 1. This is for linear theory. But what's happened when the crystal field is not so big and the crystal field is close to your microwave? But in this case, you have to use the full perturbation theory with much more possible of transition. And what's happened is in more than your allowed transition, you can have transition using, in this case, 2 photons, so 2 coherent photons, using a virtual state, and you manipulate the state that go directly to this level. It has been observed a long time ago, and using a simple Bruker EMX or LXS, you can also observe that. At low power, you have your 5 line, and you increase the power. First, you start to saturate your line, and you can see some 2-photon transition here, and even the 3-photon over here. So when we saw that, we say, oh, is it possible to do the same thing in pulse EPR? Because our purpose is to coherently manipulate this multi-photon transition. And so what we did, the first things, we try Rabi oscillation. So Rabi oscillation for physicists, or nutation in chemistry, but it's the same thing. It's oscillation, coherent oscillation of the magnetization. So this is most of the time you use it just to calibrate the microwave. This is also what we did. But if we increase the microwave power, the baseline start to oscillate, and you can see there is a new oscillation, a long period oscillation, but a new oscillation. And after Fourier transform, we observe this frequency dependence, Rabi frequency as a function of amplitude of the microwave. Usually it's perfectly linear in the first order model, but if you calculate by exact diagonalization, you have the contour plot behind, and you can detect here the 3-photon coherent transition in the manganese. So that means we can manipulate, theoretically, any levels and any transition in the manganese. Because we have a single crystal, we turn the crystal, and again, we can perfectly match between the theory and the measurement, and we can observe here it's a 1-photon, and here it's a 3-photon transition, and you can see here the compensate part is when you are in magic angle and you don't have an isotropy anymore. So this is good, but there is some transition we can't have access with only one frequency. In our case, it's a 2-photon, for example, and a 4-photon. By symmetry, it's not possible with only one frequency. So we use the Eldor option, not to do Eldor or DIR, of course, but just to manipulate 2 kinds of transition. One frequency to pump our multi-level, multi-photon transition, in this case 2-photon, and one frequency to probe the state, the final state. And this is what we observe. You observe some spot with different kind of frequency, and if you compare with the exact diagonalization theory, you can clearly identify the 2-photon transition over here, the 3-photon in the middle, and the 4-photon. The limit is 5-photon in our case, but we didn't have enough power, I guess, to reach the 5-photon transition. But that means we can have access to all electronic transition. But electronic transition maybe is not enough. And if we had the electronuclear forbidden transition, it's also possible to coherently manipulate this kind of forbidden transition between nuclear spin. And again, it was so that means we can now manipulate all electronic state and all nuclear forbidden transition state inside one manganese. So the question, what is the purpose of that? Well, you have the funny part of the science, of course, but also it's used for the Grover algorithm. So Grover algorithm is one of the quantum algorithm. And to implement Grover algorithm, you need many levels, and you need to manipulate all these levels coherently. A long time ago, it has been observed and calculated in nuclear spin, so in gallium in this case, but in our case, it's also possible. And in manganese 2+, we have access to 630 transition possible, more or less possible, but it's possible to manipulate all these states. So that means with only one ion, we can manipulate this number of states. So imagine the quantity of level we can manipulate coherently if we coupled now ions together. Pre-summary for this quantum control of large spin, we can manipulate by multi-photon coherent large spin electron spin. Using 2 microwave source, we can manipulate any transition in your in the atom, in the ion. And we can also coherently manipulate electronuclear forbidden transition, just using classical Bruker spectrometer. So now another system This time the control of the coherence. As I said, the control of coherence is very important. The longest is better, but we can't really control this aspect of the physics. And again, as I told, there is three principal source of relaxation and decoherence in electron spin: dipole-dipole interaction, nuclear spin, bath, and spin phonon. And usually the method is magnetic dilution, isotopic enrichment, and low temperature. But in this example, we go on the exact opposite. We change the paradigm and we will use the strong correlation, and very strong correlation you can have in some system. So what is a strong correlation and what is a strongly correlated magnet? Usually it's not something we study in EPR, but to understand, but in a very diluted system and paramagnetic state, the susceptibility follows the Curie behavior observed and theorized by Pierre Curie a long time ago. In this case, there is no interaction between spin. If you add interaction between spin in the 3D material, at a certain temperature, the interaction between spin is more than the temperature, and you create an order. And in this case, it's a Néel order, antiferromagnetic Néel order. But if you have also a very strong interaction, but you are in a one-dimensional system, the fact you are in a one dimension for the interaction prevents the system to order. So it remains paramagnetic even with a large interaction. And this is called a spin liquid. So the system we use is organic spin chain. It has been studied in the past, so it's not new, but I will present it to you. So in this case, it's TMTTF. Maybe some of you already heard it. Tetramethyl tetratiofulvalent for the chemist. It's a system with a very strong interaction in this direction. Each double molecule here carry a spin, so that means in each molecule has a spin, so it's the opposite of dilution. It's very concentrate. And how do you obtain it for the measurement? So for me, it's very simple. One day you receive an envelope, you open it, and you have the sample on it. But for the chemist, it's a bit more complicated. It's electrochemistry and electrogrowing, and it takes weeks to obtain very small needle. As I said, it's a very famous and old system. It has been studied in the past for 40 years now. It has been studied for a lot of physical property. At high temperature, it's metallic. At low temperature, it's insulator. Depend on the pressure and the counter anion, you can have antiferromagnetic order, you can have a spin density wave, and you can have these things called superconducting. It's a state that people think it was possible to create a room temperature superconductor using organic system, but unfortunately, the limitation was 1 Kelvin. But still, it has been studied for a long time, and the interaction inside the chain is very strong. It's 400 kelvins. It's the equivalent of 300 Tesla or 300 centimeters. So that means even at room temperature, we are below, the interaction is more than the room temperature. Let's see. And in our case, we are focused on this state, the spin pairs. And spin pairs just mean at low temperature, the system order itself by dimerization. So you have dimer with interaction between dimers, so it's strongly correlated through the chain, and it's called spin pairs. So already ESR has been done before, but of course in 40 years, I guess someone put it in a spectrometer, and it has been done in 82 by Claude Colomb, and since it has been studied again and again. So the question is, why study that? But actually, we didn't study it in purpose. I use it randomly because I need a radical for students to explain them how work EPR. And I didn't have a DPPH anymore, so I asked to a friend, give me something with radical, and he gave me this, tell me everything is known. And you will see everything is known until there is something new. So what we observe? We observe EPR line, a continuous wave EPR line, one line, like in all organic correlated system, but at a sufficient low temperature, there is a new line. Oh, very, very sharp line, less than 0.1 Gauss. And when we observe that, usually you are a physicist and you immediately blame the chemist. What is inside my crystal? And no, it's we recreate such crystal, and in all new batch, we observe this very sharp line. So we start to study it. And this sharp line have particular property. First, it can see the sharp line sees the exact same local field than the main line. We went to very high field to try to separate the G factor, but it was impossible. Up to 120 gigahertz, a very high resolution. The G factor, the local G factor, is the same than the chain. So that means this new line sees the exact same local field than the chain. But the line width is completely different. It's the variation of the line width, it's opposite between the sharp line and the main line. So that means the dynamics is different than the main line, than the spin chain. And this is something that has been think and theoretized 20 years ago when supercomputers start. And it's called breaking the perfection. The model for the spin chain is true if you have infinite spin chain. But if you break the perfection, and sometimes you break it, when you grow crystal, you don't have a perfect crystal. And what's happened is when you break the crystal, or when during the growing process there is a tilt in the crystal, this tilt, which is non-magnetic, polarized all the spin around it, creating a kind of cluster. In case of a perfect crystal, there is no magnetism. The local susceptibility is 0. But close to the defect, here, or in the middle, you polarize many spin and you create this cluster, a kind of virtual molecular magnet. And so that means we have something a bit new. We have an object made of many spins, which belong to the chain, but it's not the chain. So what we did, and with a sharp line, so sharp line will mean certainly a long coherence time. So what we did, first things, Rabi oscillation, simple, the simplest sequence ever. You apply a pulse for a certain amount of time, and you measure the magnetization. And what we observe is indeed a pretty interesting coherence time, not fantastic, but you have to imagine your system is 100% made of spin. It's really in opposite to what we think. So and each oscillation means we can manipulate coherently our state. It's indeed Rabi oscillation. And when you increase the microwave, you linearly increase the Rabi frequency. So this is Rabi oscillation. But it's the Rabi oscillation of edge state. So you have a small amount of edge state. They polarize many spin around it and create this new object, which is not a free spin. It's not a free radical, but it's not a spin chain either. And there is another aspect in this, another property. We did some field dependence of the Rabi oscillation. And we expect only one frequency of Rabi oscillation, the frequency of a spin 1/2, because the ground state is a spin 1/2. And we observed the equivalent here of spin 1, which chemically it's not possible. We only have radical. And it's not possible to have spin 1 in our system, but we observe the dynamic of a spin 1. And so what we did, we say, okay, what the origin of this spin 1? So first of all, it's on the edge. Usually when you see on the edge of the line, say, it could be dipole-dipole interaction, but still. So what we did is, with EPR, you can do a lot of things. And one of it is to measure the susceptibility. Intensity of the line is the susceptibility. And like in the squid or any kind of magnetometer, you calculate the susceptibility multiplied by the temperature, and you have the Curie behavior. In some case, in perfect Curie behavior, it's pretty flat. So that means it's a perfect paramagnetic spin 1/2. But in some of the crystal, we observe this decreasing. And when you just apply a simple model for dimer, we observe the dimer. So that's been this, a dimer, it's just 2 spin 1/2, so that's been possible of spin 1. And the quantity, which is a bit more interesting, the quantity of this dimer is not small, it's 50%, about 50%. And usually when you have some dilution, when you do dilution of ion, the probability to have a pair is very small when you have a small concentration of defect. In our case, we have a concentration of this defect around 10 to -4. So that's mean in case of a random distribution of the defect, we should have the intensity of the pair should be 10 to -4, the intensity of the main line. And here it's 50%. And the reason of this 50% is due to the 1D property of the material. It's something you can't have in 3D material. In 1D material, at the end of the chain, if you have a break, something perturbing the chain, on the other side, either you have a S = 0 dimer, or you have S = 1/2 monomer. You have 50% of chance to be in this configuration and 50% of chance to be in this configuration. So it's really something you can have only in one-dimensional paramagnetic system. And what's the interest of that? Again, let's oversell our result, but it's possible to create quantum communication. You know, a processor is made of 100 million of transistors. But if you don't know how to connect your transistor, you don't have a processor. And the main difficulty in quantum information processing is how to connect the qubit. And it has been calculated that if you have a spin chain, and if you have Alice on one side and Bob on the other side, they are naturally entangled. And this is what we expect to see. So far, it was not possible because even our temperature is too high. We need to be at millikelvin, and millikelvin is not an option with the Bruker system, but who knows in the future. But this is a possibility to entangle our two defects, which are already connected through the spin chain. So, summary of this example, you can again study in your whole spectrometer. A new mechanism of coherence protected by quantum fluctuation. The quantum fluctuation prevents any kind of transition inside the spin chain. So you have only the effect of out of the spin chain relaxation. You have a two-level system made of hundreds of spin. So it's more like a molecular magnet than isolated spin. And can we use it as a quantum wire? The future will know. Good. So I have time for my last example, and this example is completely instrumental example. In 2016, we purchased the AWG option from Bruker, and you know the new one is coming. So, but anyway, the first one, and the first time you receive an instrument when you like instrumentation, is to double check, and you check absolutely everything which should fit with your already existing result. And we had that before. So the incoherent DIR bridge, so two source incoherent, and the new one, the AWG bridge, is look like that. One source, a mixer, and the mixer managed to create all kind of frequency inside your spectrometer. And so what we expect something like that. So we measure Rabi oscillation. We change the frequency of the pump, and we should observe the famous square root of the detuning square plus microwave square, so something based in the Rabi dynamic. This is what is expected, and this is what we observed in this bridge. And we have this bridge. So what we did, the same thing. We start with delta = 0. We observed Rabi oscillation, classic, exact same result. Good. And we change then the frequency, so we increase delta. And what we observe, completely different dynamic at a certain, it's not at any, for any delta, but at a certain delta, there is much, much more radio oscillation. Oh, let's see, that means by here the relaxation appear. Here, what's happened? There is no more relaxation, we don't know. So what we did, but we have to continue. So longer time, we observe long train of radio oscillation. Keep going. We observe a very long until the TWT died. Well, it didn't die, but it was in security mode. So this is our limitation. It's just an instrumentation limitation. And you can see we were at 500 nanosecond coherence time to much more, and certainly much more than that. And so what is really inside? And you know, when you receive an instrument and you like to build your own instrument, the first things to do is to open it. Well, we didn't open it, we just connect a lot of instruments on it, and we observe what's go outside the AWG when you use it. And when you use it, you ask this frequency, and indeed this is the frequency you obtain, but you also have a lot of leakage, and you have the carrier is crossing, and the image, so the fact you have plus and minus delta. And it's not so small, and it cross everything, it enter in the cavity, and so that means your sequence is now that, and you have to take it into account. You have your driving pulse, and you have your image pulse, and you can't remove it because you don't have access to the IQ mixer in the AWG bridge. This image has the same length as the driving pulse, or any driving, even here actually. The amplitude you can control, and you can also only control delta because it's minus delta. And if you use that correctly, in our case it was a good news, maybe it's not a good news for a lot of people, but in our case it was a good news, you can clearly increase the coherence time from manganese, from gadolinium, so rare earths, from diamond. We tried everything we had in the lab. It was completely reproducible. And we have this long nutation of the spin. And it seems that the only limitation is T1, so the relaxation of the system, so the physical limit. Well, okay, we observe that, but what the origin? Well, the origin, first of all, let's do some benchmark. So benchmark is more from the community of qubit. Is can we, how to get back the magnetization after a certain amount of time. So we did it without the image. So we have the echo over here, and after some time, we destroyed the echo as expected. But with the image, we keep the echo with almost the same amplitude. We lose a bit of information, but not a lot. So that's been a very good protection. Also, it preserves the initial state. We start with state X, state Y, and state Z. And after retrieval of the echo, we observe SX, SY, and SZ with pretty intense signal and not a lot of transfer inside the other state. This is for the experimental part. Well, I will not enter in the theoretical part, but actually what you have to do is to include a dynamic part, time-dependent dynamic part. You have to solve the Lindblad-Meitner equation with time-dependent part. It takes a while even for a small computer. Or you can have this kind of Floquet engineering. It's very famous in the community of superconducting qubit. But you see, it's possible to calculate. This is the main conclusion. So that's mean, thanks to Brucker to provide such AWG. I don't know if the future one will be so good for us, but at least it will be much better for you, especially if you do LDOR, and if sometimes you do LDOR and you see some artifact, maybe it's due to the leakage of the frequency. So to finish on that, because the result was not so, was pretty interesting. So we did a small video. So if you have only one frequency, the system stay alive until the environment destroy it. And when you have these two frequency, one is used to dress the qubit. This is a name we use. We dress the qubit with an electromagnetic wave, and it's a kind of protection of the qubit. So we'll see in the future if it's useful. It seems in some part like diamond center and even rare earth is pretty interesting to use. And we'll see for the future. So the conclusion of my talk, it seems I'm in time, but it's that I would say the most exciting phrase to hear in science, the one that heralds the most discovery is not Eureka, but that's old, because each time I found something not expected, it was really interesting to study. So, and I hope for the future, even if you see something weird, don't throw it in the trash, try to study it. We have a lot of positions, so winter is coming, come to Marseille. There is a lot of place to relax and to work. And if you like my talk, we have master internship, PhD scholarship, and postdoc position. And I want to thank all my colleagues in the field and you for your attention. So thank you.
Yeah, thank you for that very nice talk, Sylvain. I found a lot of the information quite useful. So now we transition to questions from the audience. You can either unmute your microphone and speak directly, or you can throw it in the chat, whichever you prefer. I don't see any hands up, so if it's okay, I'll start with a question. When you first started talking about your Eldor experiments, I think it was around slide 28. You were mentioning the number of transitions that you can excite. Is that somehow limited by bandwidth, like in a traditional Eldor experiment, or have you
so slide
found a way around that?
20. Which slide exactly?
Yeah, it was this conclusion point you made on slide 28.
Okay. Okay. Oh yes, here.
Yeah.
Over here. Right. So this is in manganese electron spin. You have 6 level, and you have for each of the manganese you have nuclear spin 6 level too. So you have 36 level, and when you calculate the number of possible transition, actually even impossible, because nothing is impossible in spectroscopy. When you calculate, you have this kind of number of possible transition when you have enough power. And it's possible to have this kind of transition when the microwave power is bigger than the crystal field, which is not often, but in cubic symmetry, it's appear often.
Okay. But you're still using a resonant cavity? So if you try and pump on one and observe on the other, do you see a limit between which transitions you can access coherently, or is it?
Yes.
How does that work?
You're right. So because indeed you need your two frequency to enter in the cavity. So this is at minimum you need a Q factor low enough, or to have multi-mode cavity. Usually, it's the easiest way is to have a broadband, maximum power, and you have access to everything. But there is a limitation, of course. Here, our limitation is only the hyperfine interaction, because this is the main separation of line. So from the first to the last, how much megahertz? So it's pretty large. So from the first to the exact first to the exact last is difficult. But it's just a technical issue. It's not a physical issue. This is
sure. Thanks. Okay, got quite a few hands up. I think Thomas was first.
Thank you for the talk. I've just kind of a curious question, and this is just probably a background question. In the spin chain, what you presented on, how far do the spin, what's the maximum distance the spins can be apart from each other inside a chain? Or pretty much what's the density of the spins in a one dimension?
So
you still allow the effects pretty much.
Yeah, it's a good question, because it's a strange physics somehow. So each molecule carries a spin. So actually the distance between each spin, it's short, it's 1 nanometer maximum. But the distance between solitons, so that means the defect in the chain, it's much longer. The density is around, because it's at one dimension, it's 1/10,000 cells. So that means pretty large. The difficulty to connect the first to the last defect in the chain is the temperature. The temperature has to be below the correlation length. And so that means usually in such case, we need to be at 10 millikelvin maximum to really see the entanglement between the first and the last spin in the chain. Now you have also the first spin of the chain and the last spin of the other chain. In this case, we observe that the distance is not just a cut. There is certainly a small amount between them, a small amount of chain. We are around 10 to 20 spin. So that means there is a kind of communication between the 10-20 spin through an unknown chain. Unfortunately, we can't know that yet because the G factor is exactly the same. So we can't separate them by spectroscopy. But at least what we observe is interaction between two solitons distanced by 20 spin.
Yeah, but the interaction between this is what I'm trying to get at. So each spin individually is around 10 angstrom away from each other. I understand the defects on the ends, I get that. But then let's say, for example, the spins, the separation will be 15 angstrom, it will be 20 angstrom, it will be 30 angstrom apart in the chain itself. That would make the communication with the two defects, that would obviously lower the communication. Is that correct to assume?
So it's correct for the correlation, but if you are at t equals 0, the spin chain, the Heisenberg spin chain is a prototype of a Bell state. It's a perfect entangled state. And if you manage to manipulate this open chain, you have quantum teleportation, you have entangled states. It's a really interesting theoretical calculation to do, but it's proved that if you are at temperature low enough, which is extremely difficult to reach, you can have even at I would say infinite distance, it's entangled.
All right. Thank you.
Thank you.
I think the next question was from Boris.
Hello, can you hear me?
Yep.
Yes.
All good.
Yeah, thank you. It was a great talk, especially the minions was really great to explain spin interaction. I enjoy that. I have a question to your dress states. So if you go to that slide, I didn't get on which system you did that. Was it a spin chain or was some other?
No, actually, it was on any kind of system. That's why I explain it's instrumentation dress state. So it has been done. So I start just with manganese because I have it, but it's you see MgO-Mn, gadolinium, diamond. Actually, I try it also on the spin chain, but you just need a spin. And actually, it's just simply you have a spin and you have these two frequencies. One, to explain, imagine when you are in the laboratory frame, you have your two levels. When you are in the rotating frame, your two levels become a kind of how to say U in quasi-energy, and it looks like a clock transition. So you have this weird shape, and if you are exactly here and you manage to manipulate the spin inside the gap, the Rabi gap, you are in a kind of clock transition. So that's why this is a Dray state. You manipulate externally. So it's a dichromatic.
I wanted to mention, actually, we implemented this with NVC diamond.
Yes, it has been done.
Yeah,
actually, it has been done using Andor. Using Andor, you can do that. Using Andor, if you want, you can do the same thing with Andor. You turn your coil to be parallel to SZ rather than perpendicular. And with the Andor, when you have the frequency of the Andor equal to the frequency of Rabi frequency, you enter in this regime also. It has been observed 20 years ago, I guess, not for this purpose, but it has been observed. It's called bichromatic, and it's really interesting. To my knowledge, it was not observed with microwave directly, but
that's what I'm saying.
Equation is the same.
We observe in microwaves directly, although we detect optically. So I just wanted to comment on this. It was basically the same effect. Can you show
Yes.
that you had I think it is published. You had like a
For
this calculation.
this
There was
result, yes,
some
it has been
link.
published.
Sorry.
Yes, it is published.
Because
Over here.
okay, so I have to track it down then. Yeah, so we did with single NV centers, like it was 2012, I think, but it was the same idea. We were all surprised that you can go to milliseconds with Rabi oscillation. It was really really stable. And you also had this video. You tried to explain the same effect.
Yeah, it's for
like
kids.
For kids. Okay, yeah, well, it's really because I was thinking it's like the spin pair, but it's not really a spin pair in the video. Like it's more like
it's
to
just
compare
oscillation between the two states.
the dress states. I see. Okay, thank you. Okay.
Thank you.
Okay, I think Igor has the next question. Are you able to unmute?
Yes.
Go ahead.
You hear me, right?
Yes.
It's a great talk, Sylvain.
Thank you, Igor.
I'm glad to hear again biochromatic radiation, the two-photon transitions.
You will have the YouTube video.
Yeah, yes, great. I will show to the guys, and as well as turning and/or coil in parallel, all these stories, the interesting world of multiple photon transition, reset state, the electromagnetic transparency, and so on and so on. And I would also mention it's a great discovery with the Bruker AWG1, where unperfectly calibrated device, but provided you with coherent, the two frequency totally coherent source. This is the major advantage of AWG. And actually, I will even tell at Bruker that, okay, looks like there are several actually demand. Some of them, for example, for deer, don't like to have two coherent microwave frequencies because then some side effects averaged due to incoherency. But others, like your application or there are many others want to have a coherence. So actually we can provide both cases. Bichromatic, you also can, user could program it to be bichromatic, two-tone excitation and so on and so on. And so it's great, great things. And now even for quantum information. Yeah, thanks a lot.
You see, but it's due to it's a black box. So of course, you usually an IQ mixer you can benchmark it and reduce any side effect. But in the AWG, it's a black box. You can't have access. But if you build your own spectrometer, you can. It's really simple to completely remove the sideband.
But it's I'm system architect at Bruker, and AWG2 actually partially under my control. What is going? We know everything which is inside and how it make. As well, we provide a calibration.
I'm curious to see what's go outside.
Yeah. We provide also the calibration, which does calibrate and with the maximal suppression of carrier and also the phase and amplitude imbalance for lower or upper sidebands. This calibration even at factory and so on. In addition, users simply can apply user-specific excitation stimulus. Then you can manipulate whatever you like. Yeah, thanks.
That's good news. So it's good. It will be fun.
Yes.
So we had another question in the chat from Luming. First, thanking you for the nice talk, and then the question is about what is the spin correlation length of the one-dimensional magnets, which I think you touched on in Tomas's question.
So the spin correlation length will depend on dimerization. Let's go over here. Let's say maybe we can see here. So actually, the spin correlation length is highly depending on the dimerization. So if you have a uniform spin chain, so that means a perfect spin liquid, the spin correlation length is and you are at 0 Kelvin, is from here to the other side of the chain. So it's and you can calculate it. You polarize everything. In the case of dimerized spin chain, but it's converged quickly and completely depending on the value of delta. So if you have 1 plus delta J, 1 minus delta J, it's a convergence here. For example, here I think it's 0.1 for delta, and you can see the calculation in 1, 2, 3, 4, 5, in 7, maximum 10 spin, the correlation lengths really decrease. But when you have a system with a weak dimerization, or even if we manage to find a true spin liquid, whatever the temperature is, we can clearly connect one side of the chain to the other side of the chain with a very long correlation length. So yes, so that's completely depend on the dimerization of the chain.
Okay, very good. Second question in the chat, also from Luming, is how much power is needed to pump the multi-photon transitions in the manganese and magnesium oxide that you showed?
So the maximum we can have in a conventional spectrometer. So I think so. We were so yes, I remember. So in case of manganese, we are lucky because the Rabi frequency is 3 times more speed with the same power than the spin 1/2, because it's a spin 5/2. So in this case, you need a bit less power, but still we use a 1 kilowatt power amplifier from TWT. We try the maximum amount of power, and we observe that. So we have to be careful of the ringing. We have to be careful of a lot of things, but the equivalent is the classical 16 nanosecond in 6 dB. Classical, I mean, it's not. We didn't want to go higher than the 1 kilowatt. I found it's already too much for quantum science. But with a standard, you can have access easily with the classical power of the Bruker system.
Perfect. They sent in the chat, thank you. So I guess that answers both questions. Okay, I'll do a last call for questions from the audience before we close. I don't see any hands going up, nothing being typed in the chat. If not, then we close our session. Thank our speaker once again, Sylvain, for that very nice talk.
Thank you all for staying and listen to me. And if you need anything, just contact me, and I will be happy to share any video you want or anything you want.
Perfect. Those are quite some amusing animations, like Boris said. Very cool. All right, everyone. Well, look out for emails from us. We'll let you know when the next seminar is going to be. And thanks again, and hope you all have a wonderful week.
Thank you.
Bye-bye.